Very good. Welcome back. Uh, what I would like to do now is discuss the connection between entropy and probability as was developed early on by Boltzmann. You see, as I ended the last segment, uh, I was commenting on how interesting it was that both Gibbs and Maxwell had such a deep understanding of what was going on with the second law of thermodynamics being of statistical origin. And however, they didn't try or they didn't succeed in figuring out the connection between probability and entropy. Um, Now, the connection between probability and entropy is one in which it's going to be entropy is basically this thermodynamic entropy that is macroscopic. It is the entropy of a macro state, while the probability is the probability of the micro state. It's the probability of velocities, positions, momenta, all the microscopic variables. So what's really missing there is a real connection between the microscopic degrees of freedom and the macroscopic variables. It is sort of amusing that that situation, and this is like late 60s, early 1868 or so, 1870, uh, that situation is sort of analogous to the same situation that's happening today, where we talk about the entropy of a black hole, which is a macroscopic kind of assessment of the black hole. It's basically the area of the horizon, right? Um, and we do not have a really good idea of what are the microscopic degrees of freedom that give rise to that entropy. There are proposals, but none of them is uncontroversial. And so we are in the subject of black hole thermodynamics, we are basically at the same historical level as people were back in the 1870s. So coming back to Boltzmann, and for that, I'm going to need my screen. There we go. The interesting thing about Boltzmann is that he attempted really to find this connection between the micro and macro, and he did this because he truly believed in the existence of atoms. Um, Around the turn, late in the 19th century, there were very strong schools of thought that since atoms are not to be observed, they should not be parts of the description of what's going on in physics, that you just need to worry about the macroscopic variables that you want to observe, and therefore that appealing to the existence of atoms in any explanation was really more like metaphysics than physics. Well, Boltzmann disagreed wholeheartedly. He really truly believed in the existence of atoms, and that's how, well, he managed to find, by pursuing that path, find the connections between probability and entropy. So what did he do? Well, originally, the issue for him was what is probability? And as we're going to see, he had like something like 4 or 5 different versions of what probability was. And it was a pretty messy account. He didn't know. Sometimes he had several different interpretations of probability in the same paper, sometimes in the same equation, in the same paragraph, right? So clearly there is a fair amount of confusion. But at first he started with the idea that you just look at the fraction of particles in a cell in velocity space, very much like Maxwell. Then he started also looking at the amount of time particles spent in a cell, in the velocity cell. And you can see that both of these are fairly mechanical. So these are mechanical definitions. And then he continued with this mechanical approach, And in 1868, he managed to do something interesting. Remember how it was that Maxwell had a probability distribution that was uh, that gave the distributions of velocities, and the distributions of velocities were the exponential of minus a constant v squared. Well, v squared really stands for p squared. It's the kinetic energy. So what Boltzmann managed to do in 1868 was figure out the probability distribution for the number of molecules, either the number of fraction of the molecules in a particular cell in phase space, uh, or the probability of finding particles there, the amount of time they would spend there. And this he wrote as the exponential of minus p squared over 2m divided by kt. So maybe I should write it like this: 1 over kt uh, p squared over 2m. So you see that this is basically the same as Maxwell. Uh, there is the velocity square there. But he managed to generalize this to the inclusion of an external potential. So this is an external potential. And the way he did this, the methods were already now becoming more sophisticated and a little bit different. The way he did this, he said, okay, this is the equilibrium state. If it is going to be the equilibrium state, it's the equilibrium such that when there are collisions between the particles, this state becomes a fixed point. It becomes a steady state. Uh, and so while it is true that it was a great success, it is clear here that the method based on the Boltzmann equation, this is the collision equation, um, was very good. It provided good answers, but it failed to take into account the correlations that arise between the particles due to the potentials between them. So shortly afterwards, he decided to generalize this equation, and he wrote the probability for n particles. And so here I'm going to write it like this, where I have all the the particles, and the probability now is for all the particles, all n particles. You can see this in that this is the probability of the system being found in a particular cell of the n particle phase space. And this ended up being written as the exponential of minus 1 over kt of the kinetic energy for all these particles, plus the potential that includes the interactions between all the particles. Now, and of course here I should write, here I have d3x, d3p, and here I have d3nx, d3np. Now this is the crucial element here, and the important one, because now we're starting to do something very clever. We have here the one particle phase space, and here we have the n particle phase space. So these are very different animals. In fact, the question of what is the probability can be raised yet again, And so the two additional probability interpretations that arise here is number 3, the amount of time the system spends in a region in phase space. Um, so the idea is you have this region in phase space, how much time the system spends in it. The basic assumption behind everything is that if you have the system, the trajectory of the system in this 3n, 6n dimensional phase space is going to cover the whole surface with the whole subspace within this space that corresponds to a fixed amount of energy. So the system will wander on the surface of constant energy until eventually, very long times, it has covered the whole of space. Very good. This is what's called, this leads to what's called the ergodic methods, ergodic theorems. The ergodic theorem is supposed to prove that if you allow the system to move long enough, eventually it will get arbitrarily close to any point that you pick at first. So it covers the whole surface. That's the ergodic theorem. Unfortunately, it has never been proven for real systems. So the ergodic theorem is one of those pseudo theorems. It's a ergodic wish list, really. This idea of thinking of probability as the amount of time the system spends in a region in phase space, this is what gives rise to what sometimes is called the time ensemble. This is the notion of probability that Einstein used with great success in his theories of statistical mechanics. So do not dismiss these things very lightly. With imperfect tools, these great physicists managed to do amazing things. Then there was another idea that he had, which was very nice because well, it was strange. He says, well, uh, assume that a priori equal volumes in phase space have equal probability. Then the probability is basically proportional to the volume in phase space. Very good. This is actually really powerful. For the longest time, for quite a while, Boltzmann would jump from one definition of probability that was very, very based on mechanics, the amount of time you solve the equations of motion. In principle, you should be able to tell that, to another that has to do just with the volume in phase space. Notice that here we have an interesting assumption. It's called the equal a priori probability postulate. It is fairly obvious that whatever this postulate, this assumption might be, it's not of mechanical origin. Okay, you are imposing something here that is beyond mechanics. So for a while, Boltzmann would go back and jump between one and the other and confuse them until eventually it became clear that 3 is not quite necessarily the same as 4. So he then proposed the ergodic hypothesis, which is basically that 3 is the same as 4. So if you want to figure out the amount of time the system uh, spends in a region in phase space, just basically set it equal to the volume in phase space. It's a hypothesis. It hasn't been proved. Interesting. One of the features of this, one of the reasons that number 3 appears to be like a very reasonable one, just like the previous ones when you say um, the fraction of particles in a particular volume element, right? Or the fraction of particles in a particular volume element in phase space. That seems like a very, very intuitive way to proceed. So that's amount of time the system spends in a region. The great advantage of number 4 is that it is very easy to compute with. If you actually make this assumption and you compute with it, you get results. With the others, much more difficult. Very good. So let's proceed a little bit more. The other thing that's sort of like amusing about this equal a priori probability postulate, the equal probabilities to equal volumes in phase space, is that it makes a sort of roundabout connection to the theory of probability in the sense that if you want to assign probabilities, basically you have to assign probabilities to those elementary propositions. Remember those in the lattice of propositions, and then using and or, you sum and the product rules, you can figure out the probabilities for everything else. That's exactly what's going to be happening here. If you're going to assign probabilities to a die, you say, oh, the die is symmetric. Let me assign same probability to each phase. Well, if you're going to assign probabilities in a phase space, you say, oh, let me suppose that this phase space is symmetric. We will see later precisely what we mean by that and how this arises. Let us assume that this phase space is symmetric and assign equal probabilities to equal volumes. So as you see, probabilistic arguments start to creep in Boltzmann's discussion. There is a mechanical component and there is a probabilistic component. And somehow the history of Boltzmann dealing with entropy is the history of increasing the relevance of probabilistic concepts as opposed to the mechanical ones. We're going to see that next class in more detail, but for now, let us proceed. As I said before, what he needed to do was establish the connection. So Boltzmann wanted the connection between micro and macro. So what he needed was a recipe for how do you connect macro variables with micro variables. And he proposed that the connection would be at the level of internal energy. He said, I'm going to take the quantity that we associate with measurements in the lab, the internal energy, the macroscopic thermodynamic variable we call energy, and I'm going to make this recipe here, this rule, that this corresponds to the expected value of the Hamiltonian, where the Hamiltonian, let me just write it out, is then just the sum of the kinetic energies for all the particles plus all the interactions, and the probability is apart from a normalization constant. It's going to be minus beta h, and the expected value is going to be the integral over phase space of the Hamiltonian, and you integrate it. For the purposes of this discussion here, I'm not going to worry about 1 over n factorials or anything of the sort. Not yet. We will deal with that later. But basically, this is the kind of expression one would have. We're going to simplify this notation here by calling that just dz, the volume element uh, in phase space, in n particle phase space, and put the n there to remind us. And so now you can start computing. And one of the things that yes, I should mention that the beta here, of course, is 1 over kt. And so when you start computing something like this, using you can demonstrate the equipartition theorem that end up saying that the part of the calculation that has to do with integration over momenta, H uh, contains momenta, and the part of the kinetic energy is going to be given by a Gaussian. And so the integration over P can actually be done. And so the energy ends up being 3/2 nkt, that's the kinetic energy, plus the expected value of the interaction between the potential of interactions between the particles. The part that this says that every p squared, every quadratic term in the kinetic energy leads to 1/2 kt. So if you have three-dimensional momenta, you get 3/2 kt, and for each particle, you get one of those. That's called the equipartition theorem. Every quadratic term in the Hamiltonian contributes 1/2 kt to the internal energy. Very good. So here we have internal energy. The important piece, well, this is the formula that you get. I'll let you worry about the details and derive these things in homework problems. But this is the crucial equation here. This is where we make the connection between macroscopic and microscopic. Here you have the microscopic description, and here you have the macroscopic one. Have I proven this? No. I postulated. Whenever you have a theory, the theory itself is just a bunch of equations and symbols on paper. How you make a connection between those symbols and whatever you might end up measuring in the lab, that is always a matter of assumption. And hopefully, if your assumptions are right, you will agree with the experiment and you will proceed. But this equal here, that's a highly non-trivial assumption that one is making, that the object that you're going to compare with experiment, right? This is the kind of thing that you end up measuring with calorimeters and stuff like that. Has to do with this quantity here that we calculate according to certain formulas. Now, if you want to continue to make this connection between the micro and the macro, the next crucial step is what is heat? Now, this is a highly non-trivial question here when we ask what is heat from the microscopic perspective. Why is this weird? The reason is, okay, heat is whatever you measure with a calorimeters, measure temperatures, figure out specific heats, blah, blah, blah. You know, you do the standard thermodynamics experiments. Uh, but from the microscopic perspective, you say, oh yeah, heat has something to do with the motion of the particles. But now you say, wait a minute. The motion of the particles is kinetic energy. So how do you distinguish when you're looking at the system microscopically, what might end up being contributions to just the internal average kinetic energy, uh, in these pieces here, or those pieces there for the potentials? How do you distinguish those from just, so regular energies versus heat? What makes something part of the heat as opposed to part of just energies? And the way he proceeded, it's actually, of course, as always, brilliant. Um, he did it like this. Suppose that you have uh, you perform some kind of process on your system, and so here let me write out the expected value uh, for the system. Uh, for the internal energy. And suppose now we do a small change. The idea is heat uh, is something that is transferred from one system to another, right? So let us perform a little change in our system. And when we try to figure out what is the change in this small infinitesimal process, we're going to get things like, well, whatever this change is, it will be the change that arises from changing the probabilities plus the change that arises from changing the Hamiltonian. Oops. There you go. Now look at the first term here. How can you possibly change the probabilities? Well, for example, it's the kind of thing that if you could imagine changing the temperature or doing something like that, right? Anyway, there is one part of this overall change in internal energy that depends on changing those probabilities. But there is another part here that includes a change in the Hamiltonian that comes from changes in, okay, look at this, the Hamiltonian, changing the Hamiltonian, there isn't anything you can change here. The particles have all the positions, I'm integrating over all of them, all positions are valid. The mass, you don't change the mass. So this piece is not really something that you would change. So what this is telling us is that the change in the Hamiltonian is necessarily a change in the potential energies. Now, you're not going to be able to change the potential energy between the particles, the interactions. Those you cannot change any more than you can change their kinetic energies. However, if there are external potentials, those are the ones that you can actually manipulate in a process. So, for example, you could perform work on the system by squeezing it. You change the volume, right? Uh, or you could perform work on the system by, if these particles are charged and there is a magnetic field and an electric field floating around, you could change the electric fields externally, the magnetic fields. So the big contribution here was to recognize that the second term, this piece in which you are changing, oops, delta U, that second piece, this part here, the average of Pn. This is work. Why do we call that work? Because this is the part of the change in the energy that you can control by manipulating external parameters such as the volume. So conclusion, this piece contains one factor here, one component that is the due to the change in probabilities, plus another piece that is the work. And this piece is the change in the potential energy. When you have something like this an equation of this type, we're going to say, by definition, this contribution to the change in energy, the contribution that did not come from the manipulation of external parameters, this, by definition, is heat. And we're going to call this dQ. dQ is dE minus dW. So here, there you have it. This, look, it's an integration over the microscopic variables, and that is what we call heat. This is deep. It's as deep as it gets. If our assignment of energy as being the expected value of the Hamiltonian was the internal energy, the thermodynamic energy is the expected value of the Hamiltonian. If that assignment was correct, this gives us an assignment for what we mean by heat. And in fact, this is not something with which you're completely unfamiliar. For example, so here, a little aside, you might have seen in elementary quantum mechanics classes that the energy of a system in quantum mechanics, yeah, so that you have discrete states, the energy is going to be written as, suppose you compute the expected value of the Hamiltonian, there are going to be probabilities, and you multiply by the energies of the stationary states of the system. So if you want to figure out the change in the expected value of the energy, you're going to figure out the changes of the probabilities multiplied by the energy eigenvalues plus P, and here we have the, the change of the energies. Now, how do you change these energies? Well, these are the eigenvalues of the system. So if you have your particle in a box, for example, the energies are going to come from the eigenstates. You remember how you have these stationary states where you sort of like figure out how many, well, figure out what standing wave patterns you can put in a box. And one of the things that's very clear is that if you squeeze the box, the wavelengths become shorter. Shorter wavelengths means higher energy. So one of the mechanisms to produce changes in the eigenvalues is to change the volume. You squeeze the system, decrease the volume, the energy levels go up. That part is what we call work. Kind of amusing. In the quantum mechanical context, you can even do it for one particle, right? How about the other part? Suppose, and this is the part that you're probably already familiar with, suppose that you were to do these changes, squeezing of the box. Suppose that you do these changes very, 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 very slowly. Well, one of the things that happens when you do these changes very slowly for slow processes, for very slow processes, the probabilities do not change. The occupation of the various energy levels remains exactly the same. The probabilities do not change. And so for those very slow processes, the probabilities, the change in probabilities is zero. And what you might have learned in quantum mechanics is that these very slow processes in which the probability does not change. In other words, if the system was in the ground state, you squeeze very slowly, it's going to remain in the ground state. No transitions to other states. So you remain there. This is what's called an adiabatic process. If you are sufficiently slow, it is a good idea to make the adiabatic approximation, which consists in saying you didn't have any transitions to other systems. And you look, see the word is exactly the same word that we would use to describe systems, processes where no heat is transferred. So that is presumably, this is just to make a connection to some of the lingo that is used in quantum mechanics that's clearly borrowed from thermodynamics and statistical mechanics. Very good. So we have something really, really cool here. We have an expression for what heat is, and we have an expression for what internal energy is, for the two uh, macroscopic variables that we care about. So if I were to put heat, which is the change in energy, uh, minus the change, did I do this right? Let me see, just before I start panicking here. Uh, yes, let me see, this is, here I have the delta H is delta U. Yeah, I made a mistake here. Yes, it's a good idea that I caught it. Here, the delta U is inside the integral. So, I had a mistake there. I'm so sorry. That can be very confusing when one makes a mistake because you say, I don't understand what's going on. The expression here is correct. You can see it's the expected value of the change in the energy. And so I got these two wrong. That's what the work is. So if I want to write the heat and I have to subtract the work, the heat as the change in internal energy is something that we can write from this expression here. So the change in energy is going to be the change in delta T and the change in U. So this is going to be 3 halves n k delta T minus the plus the change in U minus the change in delta U, and this is dQt. So this is the amount of heat absorbed by the system when you perform small changes in the temperature and small changes in the external parameters of the system. Now, this object here is, well, it is what it is, right? But it turns out that if you divide it, I'm going to need more room here. If you take this quantity here and you divide it by the temperature, this becomes a complete differential. It is the delta of something. It's a big something, and I'm going to write the answer for what that something is. 3 halves n k log t plus expected value of u divided by t plus k log of the following messy integral E minus beta u plus some constant. So while this quantity here, well, it is what it is, but this is not the delta of anything. It is not a complete differential. If you actually divide by t, this ends up being the differential of a function. And it turns out that this function here is actually entropy. If you just manipulate this a little bit further, you get that the uh, integral of this object here, which is what will give you the entropy, ends up being given by the familiar expression, which is E over T plus K log Z plus a constant. In fact, if you were to just replace the, so let me just write that this is familiar from thermodynamics, in the sense that if you write Z is E minus beta F, where F is the free energy, then the expression that we have here is completely analogous to F is equal to E minus T S. So I didn't quite prove any of these expressions for you, but as a homework problem, I'll leave you to calculate some of this, derive this equation here, uh, call this ds, and when you integrate it, you get expressions that start smelling like the familiar formulas from thermodynamics. Very good. So at this point, what we have here is a fair description of the state of Boltzmann's statistical mechanics. Uh, uh, and what I would like to be able to do next time is take a completely different route. In this approach, what Boltzmann did was he was essentially assuming a certain probability distribution that he had sort of like invented out of nowhere. He basically had a decent idea of what this probability distribution would be in external potentials, and then he put the interparticle potentials by hand. Uh, it wasn't very clear what the probabilities would be in the n particle phase space. He proceeded, but if you make these assumptions, everything starts smelling correct. At this point, he comes up with another definition for probability, which is going to be given purely by combinatorics. You see, he's going away from mechanics and more and more and more into saying, let's compute the probabilities using just the calculus of combinations and permutations. That part, that other development, we tackle in the next class. See you then.